I'm talking about properties of neutron star crust with improved nuclear physics, where we analyze the impact of chiral EFT interactions and experimental nuclear masses on the crust of neutron star. This work is made in collaboration with Raul and Jerome here from IP2I, and also with Sanjay Reddy from IMT Seattle. So here, just to situate ourselves, what I'm talking about, here is a structure of the neutron star with its different layers. We have a core that we can share in outer core and inner core, where we have basically homogeneous matter, and in the inner core, more exotic things can happen. But I'm concentrating this work in this small region of the neutron star, that is the crust, where we have a non-uniform matter composed by some clusters surrounded by electrons, and in the crust also some free neutrons. So I divide this talk first talking about the nuclear physics that is used to model neutron stars, where I will present the model that I'm using, that is the Meta-modell, to describe the nucleon interaction. And after I also will talk about how I describe the nuclei, the finite size effects within a compressible liquid model. And then I can talk about all the physics involved in the neutron star crust that we analyze here, and some conclusions. So we are talking about nuclear physics, nuclear matter. So just to remember, so nuclear matter has some properties. For example, if we see in homogeneous matter, symmetric and symmetric matter, the energy of the matter with respect to the baron density, we have a property that is the saturation, that is this minimal here. And we can describe this structure of this curve with some expansion, like I have here. I have an energy that is given by this first term is the energy here in the saturation point, in the minimal. But to describe when we depart from saturation, we can have this parameter that show how much we depart from nsat. And we have, for example, ksat, that is this curvature, and more high order parameters. And if I want to go to more asymmetric matter, so we have a measure of this, that is sim, that is this symmetry energy, how much energy we need to make the matter more symmetric, and the parameters who measure the density dependence of this symmetry energy. And that is to present, because I'm going to use in our model. So I'm using the Meta-modell, that is energy density functional with some terms. We have a kinetic term, kinetic energy, a potential. This potential is a series expansion about saturation. In this model, we have no information about the force itself. We don't say that is Skyrme or HMF. We use a semi-agnostical approach. And just with that, I cannot guarantee that at zero density, I have zero energy equals zero. So I have a correction for low density here. The advantage of this approach is that the parameters of the model are the empirical parameters of the nuclear matter. So they have a physical meaning that I can compare, and I can talk with experimentalists to see how is the value of it. And another advantage is that it's flexible, and I can fit this model also to any existing model. I can mimic other models. And in this work, what we do is that we fit the Meta-modell to some many body perturbation theory calculations that we use in Chiral model, and for the Chiral Hamiltonians that we fitted the Meta-modell for this work. So here it's again, so the expression for the energy that I have, and I fit to the Chiral Hamiltonians, and I show here the energy with respect to the baron density. So I show not just symmetric matter energy, but also neutron matter energy. And here I normalize the energy by the free Fermi gas and plot with respect to the Fermi momentum to see a better better at low densities how it is our curves. Momentum values from the theoretical say the limit of our fit that at low under this gray band we don't trust much, not so bad, but we like it more after this band easily for. And you can see already here from model the parts from the values that are converged from these Hamiltonians. One see that I'm plotting this up to twice saturation, more or less. That's because we know Chiral EFT has a breakdown density that is one sat or two times, one or two times saturation density. And it will mean that I can use this data to constrain our low order parameters that is put here, energy, the slope, and up to the curvature. The high order are not constrained by this data. So we have to make another choice to constrain these high order parameters. And what we do, since we want to do astrophysics, is we require the parameters. Okay, so and I'm going to talk also about how we do our nuclear physics nuclei description. We could do nuclei description with some more microscopic calculations, such as Hartree-Fock. However, this is we have some phenomenological approaches to work on that. One very famous is the liquid drop model that is constructed with a leptodermus expansion around the energy of the nucleus. And we have another version that is the compressible liquid drop model that incorporates the fact of changing the central density of the nucleus as function of the nucleus itself, A and Z, mass, number, and charge. And since it is a phenomenological model, it has the advantage of being fast to compute and allows us a sensitivity analysis of the different components. So in the outer crust, for example, we are going to model the neutron star as collections of Wigner-sized cells that I represent here, with a center nucleus in the middle that is described by the mass number, by the charge, and by the density. And I can write the energy. There is a component that comes from a uniform matter, that is symmetric matter energy plus the symmetry energy. And we have some finite size effects, some finite size terms that by order we have Coulomb energy, surface, curvature, and we could have more. But as we increase, as we go more in more terms, they have less and less effect on the description of the nucleus. Therefore, we keep in this study up to the curvature energy for the description of the nuclei. And important point is that we need a equilibrium condition. So this in this CLDM, where we incorporated the fact of changing the density, it is fixed by this condition, that is the cluster is at equilibrium, the pressure it's equal 0, therefore the nucleus not collapse or expand, it stay still, and the density of the nucleus is given by this condition here, that the pressure is equal of the nucleus is equal to 0. So as I say, we are going to describe the integral of the neutron star to inside the star. We go increase the density. As we increase the density, I can introduce here a quantity that we are going to calculate, that is the volume fraction occupied by the nuclei. One nucleus occupies a volume on the cell that is given by the volume of the cluster divided by the Wigner size cell. or you can also write in terms of the baryon density, the global baryon density on the cell divided by the cluster density. So as we go more into the star, we increase the baryon density. The cluster density doesn't change much, or it will decrease. Therefore, this volume fraction will expand, will increase as we go more into the star. And as we increase the density, increase the size of the nucleus, we also have this region that we call the neutron drip, where some neutrons start to drip out of the nucleus, and we have a region that we call the inner crust of the neutron star, where we have coexisting nuclei with a gas of neutrons. So it's a cluster surrounded by a gas of neutrons in the inner crust. And as we go more into the star, so here my expression of the volume fraction is changed by the presence of this gas. And as we go more and more into the star, this to get a point that the volume of the cluster will be the same size as the volume of the Wigner size cell. Therefore, the U goes up to 1, and the nucleus occupy the whole cell. That is what we call the crust-core transition. And after that, we have a uniform matter in the core of the neutron star. We can also describe this in terms of the adiabatic index and show here how it evolves in the outer crust, where we have nuclei plus electrons, and the inner crust, where we have a presence of the free neutrons, and then to the core. And you could have also some deform, of course, in this region where we are in the approaching the core. It's reasonable to think that this nuclei will not stay spherical. It can deform in more deformed nuclei that we call pasta faces. But in this work, we didn't abort this theme. And an advantage of the modeling that we are doing here in this work is that we have a unified equation of state. That means that I'm using the same nuclear interaction to describe the bulk contribution of this cluster, the neutron matter of the gas, and the core of the neutron star. So what we do here in this equation of state with the Meta-modell and the CLDM is to model a neutron star connecting these three main blocks. So I will use nuclear physics theory. We have a link to QCD given by Chiral EFT, by Chiral EFT. We have a link to the astrophysics. That is how we constrain our high order parameters. And our CLDM model, it is also confronted to nuclear masses. We are fitting the parameters to nuclear masses to reproduce nuclear masses. So we have also this connection nuclear experiment in our equation of state. So I will describe in two main blocks our work. First, the homogeneous matter. That is this use of the flexibility of the Meta-modell to fit a set of Hamiltonians based on chiral interactions. And a second part of the non-homogeneous matter, that is the use of the CLDM and the fit of the CLDM to the nuclear masses. And our work here is to use these 8 chiral EFT Hamiltonians and this representative phenomenological force, that is the slip form, and compare these two ways of describing the matter and investigate what is this impact on neutron star crust properties. So I will start with description of the uniform matter that I said before is used to describe the bulk contribution to the cluster, the neutron gas on the inner crust, and the homogeneous matter in the neutron star core. I show you before how we fit the neutron matter and symmetric matter energy, and if I have the neutron matter and the symmetric matter energy that I showed before, I can construct the symmetry energy. That is the difference of the two curves. The symmetry energy, therefore, gives us this measure of how much energy I need to make the system more symmetric. And it's an interesting quantity to plot. Here I plot energy with respect to the baryon density, and in the right, again, normalized by the free Fermi gas with respect to the Fermi momentum. And I can compare with experiments. And the blue here are isobaric analogous states, and we see that the Chiral EFT Hamiltonians are really inside the band predicted by these experiments. While we have these new results from PREX2 that are quite, they predict higher values for the symmetry energy and also for the slope, for this inclination of the curve of the symmetry energy compared to what we expect before, and shows here a tension between this Chiral EFT and these new PREX results. And here I bring attention for a difference when we see all the Hamiltonians and compare to Lee 4 with the Skyrme model, that the Skyrme predicts symmetry energy as the same way as he predicted neutron matter that I showed before, different from what the Chiral Hamiltonians show. And we are going to see what it can impact on some neutron star crust properties. So here I show the energy in bit equilibrium. That is what we are going to need for the neutron star. The energy, will show energy with respect to the baron density and normalized by the free Fermi gas with respect to the Fermi momentum. I show here in this pink band the neutron matter predictions, just to show how close bit equilibrium is to neutron matter. Bit equilibrium, so the matter of inside a neutron star is really neutron rich. It's and it's close to neutron matter. So it predicts, and this is a region where we believe the chiral interaction it's good because it's low densities, and we are going to see the effect that can be for this curve to be so different at this point. Here I also show the pressure in bit equilibrium, and this is also interesting to check because we can compare with some constraint given by the gravitational wave measure from the binary neutron star merge event of 2017, where the LIGO Virgo community proposed this constraint for the pressure at twice saturation density. And I compare here our models and also Lee4, and we can see that this is in good agreement with this prediction, even though this is already in the close to the breakdown scale of the Chiral EFT Hamiltonians, but our models are in good agreement and on that as well. Okay, so now I'm going to talk more about this inhomogeneous matter that is used to describe the neutron star crust. So as I said before, we described the nucleus energy with a bulk term that is a uniform matter given by the Meta-modell and some finite size contributions. Without electrons is the first part that I'm going to do, that is to fit this model against the nuclear masses. So in isolated nucleus, I don't have electrons, neither a gas. So I have just a Coulomb energy, that is a energy of a charge sphere, surface energy given by this expression here, where we have a surface tension given by this parameterization, where the parameters are going to be fitted to nuclear masses, and a curvature energy, that is the curvature of the surface given by this expression, with also parameters going to be fitted to nuclear masses. And here I show the residuals of our model predictions with the experimental masses after the fit. I show two, so it's the difference between the experimental values and our predictions with respect to the mass number. I show two cases. One is for symmetric nuclei, and also for here to see the asymmetry dependence, and for isotopic chain of Z equal 82. So these big holes here, it's because we don't have Chiral effects. So this shows that. And we see here some difference between the models that it's interesting when we saw before that in neutron matter these predictions of the gravity were really converge for a given value, but here when we're talking about the nuclear masses, they are pretty different. And this band here, it's correspond to what we call the best models in reproducing nuclear masses. That is H1 to 4. The dashed line is Li4 that we already knew it was quite good to reproduce nuclei. And our two models that reproduce better is 2 and 3 that I'm going to keep this band for the rest of the pictures here. So if we have this big difference on the predictions on the reproducing nuclear masses for the different Chiral Hamiltonians here, and we know that it's not because of the neutron matter, so it had to be because of the symmetric matter prediction. That is, we see a correlation here that is, they don't predict the same thing, the same value of the minimum, and not the same value. So the order, as you see here, red, magenta, green, black, is the same as we see here, red, magenta, green, black, and the rest. So the symmetric matter, there is a correlation between the symmetric matter prediction and uniform matter for the Hamiltonians and their ability of producing nuclear masses, as we see here. Okay, so now that I analyze the nuclear physics involved in this difference on the Skyrme predictions, Skyrme and CLDM predictions, I'll go to the neutron star. So this is modeling this CLDM approach for this clusterized phase. The nuclear interaction given by the Meta-modell fitted to CLDM. So in the inner crust, where it's the most complex, we have a system composed by clusters, free neutrons and electrons. And what we do, we have an energy of each cell that we minimize with respect to the variables of the system. That is the mass number, the cluster density, electron fraction, and the neutron gas density. And when we minimize this energy with respect to these variables, we arrive to these equilibrium equations. The first equilibrium equation is the viral theorem that is in original form. It is like 2 times the Coulomb energy is equal to the surface, or now surface plus curvature. That means that the surface energy has to be at least twice the size of the Coulomb energy in order to hold the nucleus. We have mechanical equilibrium, that is the pressure of the cluster is equal to the pressure of the neutron gas that surrounded the cluster. Chemical equilibrium of the neutrons in the cluster and the neutrons of this gas, and the beta equilibrium that we showed before already, the results for uniform matter. So this is the equation of state at the inner crust of the neutron star. I show pressure with respect to the energy density, and we see a good agreement here so we can see here that the neutron matter predictions is what it matters for this beta equilibrium pressure, and a small departure from the Skyrme. And from these yellow and blue lines here are the two models that when we confronted the nuclear masses were the worst ones. And you see here they depart also from the other 4 models. I can show as well the energy of the crust of the neutron star with respect to the Fermi momentum. And we can see here again that these neutron matter properties are important. The Chiral Hamiltonians, they agree with each other in this prediction, while the Skyrme model departs from it. And I also show the sound speed in the inner crust. So this drop here is because when we enter in the inner crust, we have a reduction of the pressure because of the slope of the pressure reduces because of the presence of the neutron gas. And you see here the different predictions from the Hamiltonians and the Skyrme model. We can go for more properties of this crust of the neutron star. So, for example, the asymmetry. I cluster is the asymmetry of the cluster, the difference between neutrons and protons in the cluster, and YE is the electron fraction, the global electron fraction in each Wigner size cell. And you can see that this electron fraction is pretty well, we don't see much difference among the Hamiltonians, while we see a small difference for the Skyrme prediction. And the cluster asymmetry, there is also as here the prediction of this. I keep the band that I showed before for the H1 to H4. And here in the right, I show the U, that is the volume fraction, the volume occupied by a nucleus or by a cluster inside a cell, the baryon density, baryon Fermi momentum, where again, at least for H1 to H4, these predictions are quite well together. These Chiral Hamiltonians, while for Skyrme, it departs from the other Hamiltonians. And for the composition is where we see a difference from each Hamiltonian, and well, mainly for these four here that are the ones who didn't reproduce well nuclear masses, and the band is the best ones on reproducing nuclear masses, H1 to 4, H2 to 3. So you see here that through this observable, that is the composition, is mainly determined by symmetric matter properties, while the other ones were more constrained by neutral matter properties of the equation of state. Here I can compare again the composition. I just keep now the H1 to 4 and the Icl 4 with some really well-known crust equation of state, crust predictions. And we see here that we are in good agreement what people predict before, and also we kind of constrain a bit more when if you think in H2 to 3 here. So I came to the end of the talk. So here, just to summarize then what we did, we adjusted the nucleon meta-model to many-body calculations based on Chiral EFT interactions, confronted the CLDM to experimental nuclear masses, and predicted the neutron star crust properties. And the takeaway message is that cluster masses, charge, and asymmetry are mostly determined by symmetric matter properties close to saturation, and therefore these quantities are constrained by experimental masses. And while other observables like energy per particle, pressure, sound speed, and the volume fraction I didn't put here as well, are mostly influenced by the low density prediction of neutral matter, where we see a big difference between the Chiral EFT and the phenomenological forces. And everything that I talk today is in this reference, in this first archive. And for the ones who are more interested in uncertainties on this neutron star crust, we have also this other work here that can be interesting to read. And that's it.